Welcome back. Let's stick with the empirical methods in the forest context and take a closer look at how the algorithms actually work. I'd like to focus on the classification methods first, as these have been shown to be successful in the identification of tree species using hyperspectral data. And mapping tree species is one of the most important tasks in forest remote sensing. There are several methods we can use, ranging from simple to complex. Let's start with some of the classic ones. Discriminant analysis is used to find the linear combination of features that best separate two or more classes of objects or events. The primary objective of DA is to maximize the separation between multiple classes while minimizing the variation within each class. It's simple and effective for well-separated classes. But classic methods have their limits when it comes to more complex overlapping species data. That's where we bring in the more sophisticated machine learning techniques like support vector machines, SVM for short, and random forests, RF for short. They can either be applied to the entire dataset or after the numerous hyperspectral bands have been subjected to dimensionality reduction techniques, which I will explain right after. Hyperspectral images give us hundreds of bands. That's a lot of data. If we try to analyze all of it directly, we'll drown in information. So, what do we do when we have too much data to handle? The answer is dimensionality reduction. We take those hundreds of hyperspectral bands and combine them into a smaller set of key features that still capture most of the information. One popular technique for this is called Principal Component Analysis, or PCA. PCA takes all those image channels collected in different wavelength regions and transforms them into a new set of uncorrelated components, image channels. These components are ordered by how much they contribute to the variance in the data. The first few components typically capture most of the relevant information contained in the full hyperspectral image, with hundreds of channels. So, we can drop most of the remaining components, resulting in a much smaller dataset that still holds all important information. However, while PCA has many advantages, it also comes with a few drawbacks. Notably, we lose the direct relationship to the original wavelengths when transforming the spectral regions into principal components. This means that interpreting the components can be more challenging because we no longer know which wavelengths contribute to them. Furthermore, it can be worthwhile to visually inspect the components because in some cases, certain components might reflect irrelevant features. For example, if there are clouds or other bright surfaces in the image, they could appear as one of the first components, even though they don't carry useful information for tasks like tree species classification. Now that we've got our clean data, it's time to classify those tree species with machine learning techniques. Support vector machines, SVMs, are a powerful and easy to apply and understand method used in supervised learning, especially for classification tasks, and some others too. Think of each object you're trying to classify as a point in space with multiple dimensions. These points represent the features of the objects. For example, reflectance in different bands. Imagine you're trying to divide a group of two different tree species in a way that they don't mix. SVM draws a boundary, called a hyperplane, which is just a way of saying a line in 2D, or a plane in 3D, or a hyperplane in more than 3D. Do not even try to imagine this graphically, it will not work, but it works mathematically. The goal is to draw this boundary in such a way that the features representing each tree species are on different sides of the separating planes. There could be many ways to draw this line or plane, but SVM doesn't just settle for any random one. It picks the best hyperplane, the one that creates the biggest gap, called the margin, between the tree species. Why? Because a bigger margin means we have more confidence that future points will be classified correctly. The points closest to the boundary, those that are actually touching the margin, are called support vectors, and they're key to determining the best separating hyperplane. To find this optimal boundary, SVM needs a training set, a set of labeled points, already classified tree species. The SVM then turns this problem into a mathematical challenge, where it tries to maximize that margin while keeping everything on the right side of the boundary. Now, you might be wondering, what if the tree species just can't be separated by a straight line? Don't worry. SVM has a clever trick up its sleeve. When the data isn't linearly separable, it can transform the data into a higher dimensional space. By doing this, it tries to find a separating hyperplane in that higher dimensional space. And then it projects everything back to the original space. This method is defined as a kernel function, and it makes the whole process much faster and more efficient. Okay, time to talk about another algorithm called random forest. So, what is it? It's a non-parametric, decision tree-based method that's pretty awesome at making predictions. Since this is a MOOC about forest remote sensing, this might be misleading as an algorithm just for forest, but it can be used for any application. It's just called this way because it uses multiple decision trees, and a lot of decision trees are a decision forest. Here's how it works. Imagine you're going down a decision-making path. Each decision you take is based on a feature which will be selected by trying out all features that you have available to solve your problem. The aim at each decision step, which is also called a node, is to split the dataset into two parts or groups of samples in such a way that these two groups internally are both as homogeneous as possible, which at the same time will make them as different as possible when they are compared to each other. By repeating this step various times, we end up with a certain number of groups which contain a small amount of very similar samples that are different to all other groups. These groups of samples in these groups at the end of the decision tree branches, the so-called leaves, represent the values that will be assigned to a new sample that wanders through the decision tree branches and will end up at one of the leaves. A decision tree is a very simple model that can quite easily be calculated, even by hand. But how do we get from a decision tree to a decision tree forest? Bootstrapping, or bagging, is where the magic happens. Random Forest takes this idea of decision trees and makes it even more powerful by using something called bootstrapping. So what's that? It's a technique where you randomly sample data points from your training set, with replacement. With this, you can create a lot of new datasets with the same statistical properties as your original data. With each of these new datasets, you can train your own decision tree. So, each decision tree in the forest sees slightly different versions of the data, making the whole process more robust. So, when you combine lots of individual decision trees, each trained on a different version of the data, you get a forest. Each of these trees individually represent a comparable weak model, but when you combine them into a group, they work together to create a strong ensemble model. It's like having a team of experts who each contribute a little knowledge, and together they make one powerful prediction. If you combine decision trees with bagging, you have bagged decision trees. Now, to make bagged decision trees a random forest, we have to add one more small twist to it. In random forest, instead of trying out all features at each node to find an optimal split into the two groups, the algorithm only uses a random subset of all available features. By doing this, the individual decision trees will end up being more diverse, which helps to make the ensemble model even stronger. In summary, decision trees split your data into neat boxes. Bootstrapping helps create diversity, and random forest adds some randomness to the game to create even more diversity, which helps to make smarter, more accurate predictions. It's like turning a single tree into a whole forest of decision-making power. Alright, we've focused a lot on classification methods for forest applications. But don't be fooled, that's not the only thing. There's so much more we can do with these algorithms. For instance, we could also use them for regression, predicting continuous values instead of categories. While traditional methods work great, we're seeing a shift in the field towards deep learning, a game changer that's taking tree species classification to the next level. Deep learning models like convolutional neural networks, CNNs, can automatically learn to identify complex patterns in hyperspectral data without needing manual feature extraction. They're capable of learning from large amounts of data and generalizing well to new species and environments. However, deep learning models require large, labeled datasets to train effectively. The more data you have, the better the model can generalize and handle new situations. But how can someone evaluate all these approaches? Well, performance is typically evaluated based on metrics such as accuracy, precision, and the F1 score, which help determine how well the model distinguishes between different classes, meaning how many of the observed classes match with the predicted ones. Okay, summing up. In order to get the most out of your data, the overall workflow for the retrieval of forest traits using imaging spectroscopy data consists of pre-processing of the spectral data to remove noise and correct for atmospheric effects, possibly selecting appropriate spectral features or indices that correlate with the target forest traits, or applying dimensionality reduction, applying suitable classification or regression models, validating the results with ground truth data, and finally, interpreting the outputs to derive meaningful insights about forest structure composition. And there you have it. You're now equipped with the knowledge of how hyperspectral remote sensing and dimensionality reduction help classify tree species. The next time you look at a forest, remember that each tree has its own unique spectral signature, waiting to be uncovered. And who knows, maybe you'll be the one to solve the next big forest mystery. Thank you, folks. I know that was a lot, and I think that some of the concepts I explained above do become a lot clearer when you actually work with them. So let's go and try some analyses yourself in the next lesson.